much. So the topic of hull maintenance and biofouling management is receiving a lot of attention. It was a very interesting presentation from Tom, and especially now that we need practical solutions and proven solutions towards the targets of 2030. So the purpose of this presentation, thank you, is to look at the common biofouling management practices right now and highlight their limitations, and also try to suggest an alternative approach to the problem, a more preventive and maybe a more sustainable approach. And the guiding principle here is that we need to keep the hull clean, but we need to do it in a responsible way without sacrificing the protection of the oceans. We call it here emissions to sea, even if that part is not regulated yet to the same extent. So why this discussion is important? There are a lot of numbers out there. I would like to mention this study from IMO, the Glow Fouling report. Even a light layer of slime with 50% coverage could trigger 25% of increase in CO2 emissions. And this is based basically on surface roughness levels attributed to different biofouling types. And also when you have a dry dock on the right side, when you have a dry dock with a low-grade antifouling, within 1 year, depending of course on the trade, you may end up with more than 20% power increase due to the biofouling penalty. And this may go to 40% in year 4 and so on. So if we have a bulker of 40,000 deadweight tonnage, as you can see here, with an average consumption of 20 tons per day, in year 4 we're talking about additional 8 tons. This equals to 25 tons on CO2 on a daily basis. These are very big numbers, and in terms of CII, we're talking about going from rating B to rating D in many cases. I think the market is aware of these things. There is this push from IMO, from the short-term measures, but also charterers are increasingly involved here. They are reporting the emissions of their time-chartered fleet, the logistics operations. So what we have seen in recent years is that more and more ship operators and owners are adopting high-performance coatings. Now, when we talk about high-performance coatings, we also mean that we have more biocides that are leached and released into the marine environment. These are self-polishing coatings, and biocidal coatings represent a big part of the market. Now there are growing concerns over the harmful effects of these paints. There is of course water pollution from the release of the copper compounds, not only because of the working mechanism of these products, but also because of the cleanings, the repeated cleanings. And of course, regulatory focus has been on the air emissions for the last few years, but as new alternatives, viable alternatives are emerging in the market, regulators may need also to push for stricter restrictions on biocides. This is an ongoing discussion, but what we have now in our hands, and this is something that many owners have been using, is the biofouling management guideline, which is adopted by IMO. There are two key elements in this biofouling management plan. This is a ship-specific plan, of course, but there are two elements I would like to emphasize. We're talking about constant monitoring of biofouling with frequent inspections that can trigger the action for cleaning. And we're also talking about proactive cleaning. It is recommended as a preventive measure, which means basically clean at microfouling level before FR20, which means light slime, to prevent harder fouling from accumulating. And this is crucial because even light slime can have a negative effect on added resistance. Now, how grooming is different from cleaning. Cleaning is reactive. It's done when the vessel has already heavy fouling that needs to be removed, and usually by divers. It damages the paint, so increases the roughness, and also removes part of the paint. So we have thickness loss, we have biocide release, these things needs to be captured and disposed. While the grooming approach is more proactive, we're talking about periodical removal of slime that will not degrade the coating, but it should be applied to durable, mechanically durable coatings that are designed specifically for this purpose, to be cleaned. And of course, biocide-free coatings, so we avoid the water pollution, the risk of water pollution. Now, on the right side, you can see also a large-scale test by the Florida Center of Biofouling Control. They have coated plates immersed for 5 years in warm waters, basically, to mimic the static condition of the ship. And then they took measurements, DFT, thickness, and average hull roughness measurements. And also they're doing inspection to check the condition of the coating. So you can see that the ungroomed coating became fouled. We're talking about repeated cleanings here, so fouling accumulates again. And also we had a significant reduction in the thickness, which also says something about the copper release into the water. And at the same time, there was increased roughness that was measured in this case due to the repeated cleanings and the paint damage from these cleanings. Now, in real-life operation, what we are seeing, and I think everyone will agree, is that the cleaning approach is basically used more as a reactive measure, and it's done on coatings that are not designed to be cleaned. Silicone, for example, is very soft and prone to mechanical damage. And some of the common issues that we try to summarize here is that cleaning may come too late because there's no monitoring and there's no frequent inspections, so there's no trigger for the action. And we see also the other extreme, too much cleaning, so there's no anti-fouling paint left in year 3 or year 4. And of course we have the limitations with the divers, paint may be damaged because they're not using the right brushes, availability issues, and of course you're not allowed to clean in many ports. So the result is always that we have damage in the paint. The paint is removed, so we remove basically the anti-fouling property of the paint. We shorten the lifetime, and we also release toxics in the ocean. Now, what we believe, and we are working on this for the future, is that we want to tick all the boxes that we see here. So we need low friction surface, so we have the fuel savings in the beginning, after the application, zero biocides, minimum degradation over time, and no disruption in the operation, which basically means save time from cleanings, even if the niche areas need to be, you need to have some manual intervention. So how to get there, and especially in demanding trade profiles and conditions with long idle periods, we believe that we need two components. A biocide-free coating that is ultra smooth, so you get the immediate effect out of dock. You need superior fouling release properties that will not allow fouling to settle and attach. But at the same time, we need a hard, mechanically durable surface that can be cleaned. And this in combination with grooming robots. And basically here we're talking about a robot which is inspecting the hull frequently, similar to what Tom mentioned earlier. They clean at microfouling level. The hull is always free of slime with this approach. Now, how often this depends on the trade and the vessel utilization and the speed. As a rule of thumb, we see on a monthly basis for a low activity, low speed vessel in high fouling pressure. The idea basically here is to clean before you see a drop in the performance, because 10% overconsumption, which means that you may have fouling higher than the FR20, which is the slime level. And the robotic technology, we need to admit that it's not there yet. So we need, it's a technology that is maturing. It's a learning phase for all of us that are involved in this. Some of the basic requirements I try to list here. So it has to do with the brushes, with the force applied on the coating. It needs to be inexpensive to have a fast payback. It needs to be reliable, easy deployment. You need to be able to clean while in transit. You need to have a camera, so you have a log as a proof to port authorities when you need it. And the crew involvement is key. They need to know when and how to use it. This is very important. Of course, we as a paint supplier, we can help and ask and tell them when to inspect, because we can provide the fouling risk predictions, so we can trigger this action. Now, the current status is that we do have a number of vessels on trials, very promising results, and we will soon share with the community, so you are able to see. And we are testing different grooming technologies and the impact on the coating and the environment, so we can select our partners. I would like to emphasize as a last thing here that not all hard coatings are the same. Not all hard coatings can do this job. Here we're talking about a hard foul release technology, hybrid patented technology that combines what I would call the best of both worlds, which is basically the smoothness, the static anti-fouling property, the self-clean, the fouling release property of the soft foul release coatings like silicone, for example, and together with the mechanical durability of the more hard epoxy-based coatings. And these are 4 criteria that need to be met and verified with third-party studies and tests. These are the results of our own studies for our own product. I would like to mention there is a very interesting hydrodynamic study that was done at the University of Strathclyde. It is publicly available and you can have a look. The hard coating, hard foul release coating showed 8% power gain versus the self-polishing coating and 4% power gain compared to silicone coating. This was based on a flow channel experiment where we measured the coefficient of friction. And there was also a very interesting test on resistance to grooming, the mechanical durability. So we tested the resistance after 10 weeks idle period. And this is where the hard coating had a significant advantage over other coatings, because we saw no damage at all after repeated cleanings. This is just an example of vessel performance data. It's an example of a RoRo vessel where we see the speed and consumption 6 months after the docking compared to the same period in the previous dry dock, where we had the vessel coated with a freshly coated coating. And we saw 9% fuel savings on this case. So very briefly, a few things about us. We are a marine paint maker, headquarters in Canada, a global presence. We focus only on hull coatings and propeller coatings. We started with propeller coatings, where we saw significant savings compared to other practices like propeller polishing or also silicone coated propellers. GIT stands for Graphene Innovation and Technology. Why graphene? Our founders started from material science. They started with experiments on graphene, this material, 10 years ago on the aerospace applications. And this material is very interesting because it's 200 times stronger than steel, and it is used in our formula to enhance the performance. Of course, it's not only graphene in the formula. And in the Greek market, we are represented by our good partners, MIS. So thank you very much, Mr. Le. Thank you.